Hello. So we are going to do, we're moving on to our geometric sequences. Our last lesson dealt with arithmetic sequences, and arithmetic sequences are repeated addition. Either you're adding the same number a bunch of times or you're subtracting the same number a bunch of times. Here, geometric sequences are a different type of sequence where we're talking about repeated multiplication. So I would like for you to write somewhere up top something along the lines of repeated multiplication. So repeated multiplication, as an operation, if we're multiplying by 2 times 2 times 2 times 2, that would be 2 to the something power, right? So x times x times x times x is x to the, I don't know, how many did I say? 4, x to the 4th power, right? So a geometric sequence, if we're talking about repeated multiplication, looks, because it is, like an exponential function, where our unknown, our x value, n, tends to be what we're talking about with sequences, but our unknown, our variable, is in the exponent. So some examples of geometric sequences would be as follows. A very straightforward one would be 7, 14, 28, 56, 1, 12, 2, 24, ... Okay, so with this guy, we know that it's repeated multiplication because we're multiplying by 2 every single time. We have a first term, which is 7. We have a common ratio, which is 2. So whereas with arithmetic sequences where we had a common difference, D for difference, we have a common ratio here, which is R, which will be a part of our formula. Realize, in order to find your common difference, remember that difference means subtraction, that you would just subtract two terms together in order to get your common difference. A ratio is a fraction, right? So in order to find our common ratio, if it's sometimes, because sometimes with geometric sequences, it's harder to tell what your common ratio is at first, just take two numbers and divide them out. If you're told it's geometric, take two terms that are sequential and divide them out, and it will give you what your common ratio is. Always double check that you divided them correctly, which you can do by looking at, am I getting bigger or smaller? If I'm getting bigger, then my ratio should be larger than 1, right? If I'm getting bigger and bigger and bigger, it should be at least like 1.5, 1.1 in order to get bigger. If I'm less than 1, like a half or 3/4 or a fourth, I'm getting smaller every time. So make sure that you're just keeping in mind the general picture of what's happening here as you're calculating the common ratio. Okay, here we go. The next one that we're going to talk about, or the next example, is this one. This is a good example of how it's kind of hard to tell at first when you're looking at this term to the next. If you're not told that it's a geometric sequence, you might think that this is an arithmetic sequence. But then what if I said that the next term was this? Then that throws a wrench into what your thought was of like, oh, it might be arithmetic, because that's not arithmetic. Our first term is 2. Our common ratio is, here you can divide out the terms if it's hard to see. In order to get from 2 to 5, I had to have something larger than 1. So I wouldn't do 2 divided by 5, because that would be less than 1. I would do 5 divided by 2. And then think about that. Okay, well, what if I multiplied 5 by 5 divided by 2? That's 25 divided by 2. What if I multiplied 25 divided by 2 by 5 over 2? That would be 125 divided by 4. So our common ratio here is 5 over 2. The last example I'm going to give you is another one that throws some students for a loop, is when we have alternating signs. If you just looked at the numbers and ignored all the signs in front of the numbers, you could notice going from 48 to 24 to 12 to 6 to 3 to 1.5, you're dividing by 2 every single time. How we represent that as a common ratio is a fraction. Instead of saying dividing by 2, we're going to say we're multiplying by a half. However, since there is that negative symbol there, that negative sign happens because our common ratio is negative. If I take a positive and multiply it by a negative to get from positive 48 to negative 24, that would work that way. And then to get from negative 24 to positive 12, I'm multiplying by a negative again. So you're doing a repeated multiplication of a negative number, but it's the pattern and the behavior of negatives multiplied by negatives and then negatives multiplied by positives and how those all play together that create this really funky pattern. But it's just because your common ratio is negative. So our first term here is 48, and our common ratio is negative a half. Now, geometric sequences and arithmetic sequences are not the only sequences that are out there in the world. They're just the more common and applicable sequences that are out there. So like in the analysis class, they might delve into all the other types of sequences that there are. But since we're talking about applications here, arithmetic and geometric are ones that you'll find in very common ways. Interest, medicinal doses, depreciation of things, whether it's value or half-lives of trace amounts of plutonium in something. I think that was correct. I'm no scientist, but okay, so we need to have a formula. This formula is in your formula packet. It's just below your arithmetic sequences, labeled geometric sequences. How we find it is very similar to how we found our previous formula. Remember that we started with u sub 1, our first term. Well, our second term is our first term multiplied by this common ratio. So then our third term would be our second term multiplied by this common ratio, but we've already defined what the second term is. The second term is the first term multiplied by the common ratio. So I could replace u sub 2 with u sub 1 times r, but don't forget that we are now also multiplying that by r. This is u sub 2. So I just did a substitution there. And then I can combine like terms. R times r is r squared. Okay, so then u sub 4 would be u sub 3 times r. Sorry, my u's look weird. Okay, and that equals u sub 1 times r squared times r, which is u sub 1 times r to the third power. Recognize what the pattern is between n and your exponent. Very similar to what we saw with our arithmetic sequences. When this guy is 4, this guy is 3. So it's 1 less. And that'll hold true for all of the terms. U sub 5 will be u sub 1 times r to the fourth power. U sub 6 is u sub 1 times r to the fifth power. So our formula is u sub n equals u sub 1 times r to the n minus 1. Ta-da! And that's geometric sequences in a nutshell. Okay, so we're going to find a geometric sequence with our first term as that and our ratio as the other thing. So we can just put it all together. Write down your formula at the top first, always a good practice. A sub n equals a sub 1 times r to the n minus 1. So then a sub n is equal to 2 times 3 to the n minus 1. And there you go. It says to describe this sequence, which means to write a formula for it. So that would be another phrase to ask you to write an equation for this guy. And so our first term is 1. Our common ratio, we are dividing by 2 every single time. In other words, we're multiplying by a half. So our common ratio is a half. So putting that all together, we would get a sub n equals 1 times a half to the n minus 1. This is a half-life formula. So when you're told that a half-life occurs every certain number of years of something that depreciates over time, that's it's an exponential function with your base as a half.